So when we cut a magnet, we get two magnets with each one of them having both a north and a south pole. The question arises, what if we keep doing this? What if we cut it even further? Okay, the thing is, the more we cut it, the more magnets we get, and each one of them has a north and a south. So one might ask, when is this going to end? What's the smallest magnet that we can possibly have? So to talk about that, we go all the way to the level of the atom. As we will see in this chapter, magnetic fields are created by moving electrical charges. To have a magnetic field, you need a charge that's moving. And if we look at the level of the atom, we have moving charges. We have electrons that orbit the nucleus of the atom. So that is actually a moving charge that results in a magnetic field. In addition to that, there is a spin. Each of the electrons is going to have a spin. The spin is a motion of charge. So the spin itself results in a magnetic field. Or in other words, an electron, just an electron by itself, due to its spin, is going to act like a magnet with a north and a south pole. An electron orbiting around the nucleus associated with the orbit, that's different than the spin, but associated with the orbit is going to act like a magnet as well. Now, however, the situation is a little bit more intricate. Consider, for example, this particular atom where it has two protons and two electrons. The way electrons are paired in orbits in atom, you have one of them spinning in one direction and the other spinning in the opposite direction. As a result, as they orbit, one is going to orbit the atom, the nucleus, in one direction, the other is going to orbit in the opposite direction. As a result of that, the magnetic field due to both of them are going to be opposite and are going to cancel each other out. As you notice here also, we have the same issue with the spin. The spin of this one is up, the spin of that one is down, meaning the magnetic effect of both electrons are going to cancel out as well. In atoms, where I have one electron in the outermost shell, or what we call an unpaired electron. So this is a poor example in terms of a graphic, but I didn't make the graphics and this one was available. But then you can have an atom with a lot of protons, a lot of neutrons, and then a lot of electrons, but then at the end, you are going to have one electron that is unpaired. That electron, if it is unpaired, then it's going to contribute to the magnetic field due to its spin and due to the orbit, due to the fact that it is going around in the orbit. Now, that particular atom is going to act as a small magnet. When you think of matter as a whole, usually we characterize it magnetically as one of three types, what we call diamagnetic, paramagnetic, or ferromagnetic. All matter is supposed to be diamagnetic. Now, these characterizations are based on the way these matters or these materials interact with an external magnetic field, meaning if we subject them to a magnetic field, what are they going to do? In the case of diamagnetism, what's going to happen whenever we subject it to a magnetic field, they are going to oppose that particular magnetic field by inducing a small magnetization that is very, very weak, but that is opposite to the applied magnetic field. Okay? That's diamagnetism. Okay, very much this is a simplified description, but that's the bottom line. In the case of paramagnetism, it's not going to be in all materials. It is stronger than diamagnetism, but in this case, the magnetization is proportional to the applied magnetic field. It's going to be proportional and in the same direction. However, the minute you remove the field, then the magnetization goes to zero. Okay, so that magnetism and paramagnetism is going to be present only when we have an external magnetic field. In the case of ferromagnetism, it is very strong, resulting in magnetizations that can be larger than the applied magnetic field and also in the same direction. Ferromagnetic materials are the materials that have unpaired electrons in the outermost shells.